Hi, and welcome to another algorithmic modeling challenge. In this one, what I'm going to do is, given a curve that we're going to think of as the thread inside of a pearl necklace, I would like to implement an algorithm that populates that thread with a bunch of spheres that represent those pearls on top of the thread. All right. I'm going to do it in two different ways. One is going to be given the set number of pearls, and what we're going to see is this algorithm doesn't really quite make them fit perfectly to each other. They don't make them. It doesn't make them tangent to each other, but at least it fills up the whole curve all the way up till the end. So that's going to be one way. The other way is going to be by implementing an algorithm where we control the radius of those spheres and we constrain them so that they're always perfectly tangent to each other in one point. With the drawback that we cannot control that they will fully complete the whole thread. So there will be always some leftover curve after those spheres. So this video is going to be for beginners in Grasshopper. So I'm going to assume no knowledge. I'm going to explain everything very carefully, and the algorithm is actually quite simple. We're going to be using only a handful of Grasshopper native components. If you're interested in a more advanced interpretation of this exercise, part 2 of this video will be how to implement these same algorithms using C# scripting, and part 3 hopefully will be how to implement this in a way so that we can optimize iteratively, generatively this algorithm, and we can find a combination of the amount of pearls, the radius of those pearls, and the fact that they're tangent to each other so that we minimize the leftover curve. And we're going to do that by applying optimization using Galapagos in Grasshopper. So that will be part 3 of this video. All right? So shall we get to it? Okay, so let's get started. But before we get into implementing any code or like throwing in any components in Grasshopper, it's very important that we spend some time thinking through the problem, thinking through what we have as inputs, and what is the process that we're going to follow to get to the result that we intend. So here, in the problem is we want to design a pearl necklace, and that is going to be populated over, for example, a curve that we have in Grasshopper, in Rhino, from whatever. So in that case, we have to think that our inputs are going to be a curve. So we do have a curve, and we want to put a lot of pearls, so spheres on top of them. And the other input that we're going to work with is the number of pearls. So how many pearls do we have in this pearl necklace? And what follows is that if we also assume that these pearls are going to populate the whole curve, then the question mark that we have right now is how big should those pearls be? What is the radius of each one of those spheres that we're going to populate over the curve? So the process that we're going to follow is going to be super simple. The first thing that we're going to do is we're going to divide that curve in an amount of points equally distant to each other, an amount of points that is going to be equal to the number of pearls. All right? And then we're going to place spheres on top of them. But what we need to know first is like how big those spheres are going to be. And for that, we need to follow a simple rule to find the radius of that pearl necklace. And I'm going to give you like 2 seconds to think about that. So pause this video, think about how you would do it, and then come back. Thinking. All right, enough thinking. So it's going to be very simple. If we have the curve, from that curve we can calculate the length. All right, and then if we have, for example, five pearl necklaces on top of this curve, what is very simple to find to see that the radius of that of each one of those pearls is going to be the length of the curve divided by the number of pearls minus 1. Because imagine you have 5 pearls. what you want is you want to divide the curve in 4 segments, because 4 segments are the segments that are in between 5 elements. Just as if you had 3 pearls, what you would have is 2 segments between those 3 pearls, right? And then we're going to multiply that by 0.5 or divided by 2, because the radius is going to be half the distance between those between those 2 points. All right. So it's going to be a very simple numerical rule, this one here. And you're going to see that implementing this in Grasshopper is very simple, because we do have components that give us the length of the curve, that subdivide a curve into a family of points, and we can do this numerical rule very simple. Okay, so let's give it a try. Cool, let's get hands-on. So what I'm going to do is, on the Rhino side, I'm going to come here and I'm going to create a point from control points. So for example, something like this, like this, like this, like this. A curve that I could use as the baseline for my pearls, right? I can rotate around here, and you can see that right now it's a planar curve, but I could, for example, just take one of these points and drag it up, and I could make this curve volumetric, so I could give it like spatial, which we don't need, but it's totally fine. The algorithm is going to work anyway. And then I'm going to come here, and what I want is to bring my geometry in Rhino as an input into Grasshopper. And the way to do that is by using the primitives, so the parameters. So here in the first tab, in the parameters tab, if I go to geometry, you can see that I have all these empty boxes here that can hold information either passing through it or manually loaded from Rhino, which is what I'm going to do right now. So here I'm going to go to the curve parameter. I'm going to drop it here. And then you're going to see that right now it's orange because it's empty. It has nothing flowing through, or it has nothing loaded into it. So what I'm going to do is I'm going to right click on here. I'm going to do set one curve, and then Grasshopper goes away, and here is asking me to choose the curve that I want to reference. As I click on this curve, right now this curve has been referenced into this component here, and from now on I can use it down as a parameter, as information that I can use in Grasshopper. And you can see that if I drop a panel and I connect it to the curve, I can see that I see my reference curve. I could also empty this, so clear values, and now it's just not referencing anything. I'm going to undo this and bring back the curve. Okay, so that's going to be the first parameter in my Grasshopper definition. The second one is going to be the number of pearls. And for that, I'm going to need a slider, so I can go here to input, number slider, and drop a number slider here. The only thing that I would like to do is I like to customize a little bit this slider, because by default they go from 0 to 1 with 3 decimal spots, and for the number of pearls, this doesn't really work, because I know that I probably want more than one. That's for starters, but also most importantly, I know that the number of pearls needs to be an integer. It needs to be a number with no decimal part. It doesn't make sense to have 1.23 pearls on the necklace. So I want my slider to force the accuracy to be natural numbers, aka integers, so numbers with no decimal part, and I'm going to move the maximum, and I'm going to go, for example, for 100. Also, I don't want negative, because it doesn't really make sense in this case. And now I have a slider here from 0 to 100 that I'm going to customize also the name, because it's just good practice. So number of pearls, for example, right? And that's pretty much it. Now, these are going to be the two inputs that I'm going to work with. I'm going to group them to make things a bit more clear. And now I think I'm ready to start developing the two parts of the algorithm that I described. One of them taking the curve and dividing it in so many points as the number of pearls, and the other part calculating the radius. So let's take a look at that. The first part is going to be super simple. I'm going to go all the way up here to the curve tab, and in curve I have division and I have divide curve. This component, if we take a look at the component, this component takes a curve and divides it into equal length segments. So, and the inputs are the curve that I want to divide, how many segments I want to divide it in, and the split, whether if I want to split at the segments or not. So for example here, if I take this curve and I plug it in here, now I'm dividing it into 10 segments, which gives me 11 division points. So, and then you can see that if I scroll this over, I get more or less points, all of them being equally distributed along this curve. All right. So if I want to be very rigorous about this, I need to keep in mind that since this component divides the curve into an amount of segments, all right, 1, 2, 3, 4, 5 segments, right now this component is giving me 6 points. And I can see that if I plug in here, I can see that it's giving me from 0 to 5, it's giving me 6 points. So that is not exactly the number of pearls. So what I will need to do is I will need to say, if I want 5 points, what I will need to do is divide the curve in the number of, in 4 segments, aka the number of pearls minus 1. So what I can do is I can place here, I can go to the Math tab, go to Operators, and choose a subtraction component that I will use, and that I will use to take the number of pearls, subtract it by the, and subtract 1 unit from this value. A way to do that is I could choose a slider to put it here and then just set it to the value of 1. However, I don't really like that because I feel that whenever there is a slider, then there is the tendency to move it around and change it. And I don't like, this number must be 1 always for the algorithm to work. So I don't want any user accidentally changing this number and then messing with the result of my definition. So a very popular technique to do that is just using panels, not just for visualizing information, but for inputting that information. So I'm going to drop a panel and write the value of 1 here, and then plug that value here into the subtraction. We can see now that the output of this component is the number 4 that I can plug in here, and then now I do actually have 5 points in my curve because I have divided it in 4 segments. Okay, so with that, I think we are good for the division of the curve. I'm going to group this. Okay, and now I think we're ready to now try to figure out what the radius of the spheres should be. But before that, why don't we just place some spheres? So I'm going to place here, this is from, you can go to the Surface tab, you can go to Primitives, and then here you can find a lot of different ways of creating spheres. I'm going to choose a sphere from the center, like the basic one. And if I plug all these points here on the sphere, you can see that that now they're all placed on top of the curve, and that if I were to plug a slider here, I would be able to change the radii of each one of those. But I want the radius to be not some value that I choose. I want the radius to be a smart value that is coming from the relation between the pearls and the length of the curve. So that's why I'm going to do some arithmetic to figure out what the radius of these pearls should be so that they don't overlap like this. Okay, so and as per the diagram that we did before, this one, the rule is going to be this one that we have here. The radius of these pearls is going to be the length of the curve divided by the number of pearls minus 1, which I already have there, times 0.5. So let's take a look at how to do that. The first thing we need to do is we need to find the length of this curve, and that's also very easy. If we go to the Curves tab, and if we go to Analysis, we can see a lot of components that analyze and give you information about curves. One of them being, for example, length here. This component measures the length of a curve. So if I plug this here, and I plug in the curve that we already have somewhere here, right? Then this is going to tell me the length in whichever Rhino units I'm using of this curve. So if I were to now divide this number by n minus 1, so the number of pearls minus 1, just like I have it before, here. So I can go to math, and I can do operators, and I can do division, or I can just double click here and type division, and I'm going to divide the length of that curve by n minus 1 pearls. That gives me a number that is going to be 2.69. And if I were to use that value as the radius, what we would see is that the pearls are overlapping on top of each other. And very interestingly, you can see that the overlap is actually almost exactly going and hitting the other point where the next pearl starts. That's because, again, that subdivision, that division that we just did, gives us the diameter. So the only thing that we need to do is we need to divide this number, again, we need to divide it by number 2, or we need to, so I'm going to copy and paste this panel here and just change it to the value of 2. And that gives us this number here. And then that is the value that we should plug in here. We can also multiply it by 0.5, whatever, both of those work. And now we do have the right value there. And very nicely, if we now change the number of pearls, you can see that the pearls start growing because they start adapting to the length of the curve. And if we start increasing the value, they also start shrinking, because the value of the radius is now it's parametrically linked to the length of the curve. And you can also see this because if I were to ridiculously enlarge this pearl necklace, you will see how the radius, how the size of all these pearls increases a lot as well, you know? Okay. And I think that's it for this algorithm. This is the calculation, and this is the sphere. And I'm going, yep. So this is for this part of the algorithm. One thing I would like to mention is the fact that the algorithm that we have designed roughly creates a pearl necklace where all the pearls are roughly tangent to each other, but they're not exactly tangent to each other. So it wouldn't be real in the sense that some of the spheres are overlapping on top of each other. And we can see that if, for example, right now the curve has volume, if we look at the top, you can see that there are areas where the spheres are overlapping with each other, right? Like just like here. And we could think that this is maybe because the curve has volume, so we're seeing the projection of that. But if I were to create, for example, if I were to create a new curve with a very ample curvature, but then here I have a very small kink, like a very sharp kink, and this curve is right now flat. If I were to do that, we can see that you see all these curves are overlapping on top of each other, not only because of the proximity of the curve, but actually just because the algorithm that we have designed doesn't really take into account when a curve is the angle is very acute. So in order to do this, there is a different method that we can use in Grasshopper for subdividing the curves, and that is going to be here on the curve subdivision. Instead of dividing the curve among equal length segments so that this segment here is equal length as this one here, and therefore that's why we have the problem. This point is too close to this other point. Instead of that, there is this other component called divide distance, where what the component does is kind of what the icon is showing. It just finds the next point along the curve that is at a linear distance between the previous one. That means that if we want all the pearls to always be tangent to each other, then that is what we need. We need linear distance between them. So the only problem with this is that since we don't know the curvature of the curve, we cannot apply the same logic we just did. We cannot say I'm going to divide the length of the curve by the number of pearls, and that's going to be the radius, just because since we don't know the curvature, where these points, where the centers are going to be placed along the line, is not at constant lengths, and therefore we cannot perform that division. So for this one, the actual algorithm would be different. We would not start with the number of pearls. So we would start with the radius of those pearls, and then however many pearls pop up, it's just going to be a result of the shape and the length of that curve. So I'm going to plug in here the curve, and then I'm going to create a new slider. I'm going to double click, or I'm going to go here, I'm going to drop a slider, and I'm going to change this value from 0 to, for example, 10 units, and I like the 3 decimals. So I'm going to place that here. This is going to be the distance between those. And this took a long time because I need to perform a lot of calculations. I'm going to hide the points before. I'm going to hide these ones here. I'm going to do that by clicking with the middle mouse and disabling the preview. Okay. And now you can see that here I have all these points. I'm going to increase the length a little bit, 10. Can you see how interestingly this point here, this one is very far away along the curve from this one, whereas the length of this segment is probably much longer than this one here. So if I were to now double click here, press sphere, so that I can place some spheres on top of these points. And what is the radius of those spheres going to be? It's going to be equal to the distance between these points, the linear distance, okay, divided by 2. So I'm going to do a division. Here I'm going to place a panel. So I do double, a shortcut is to double click and do 2 forward slashes. I can drop a panel here and I can divide this by 2. And this is the radius 5. And if I plug that into the component, you can see that now if I have a top view, you can see that all the pearls are perfectly and exactly tangent to each other, especially on the areas where there is like a weird curvature. This would also not be real because the pearl would probably not, the cable, the thread going through them would not be leaving the pearl, but you get the point. So if I were to do 5, for example, you see that now linearly, one after the other, this overlaps because they're in different threads, but at least the one before and the one after is exactly on the right place. But you also see that we always will have like a small remaining length after this. This is just part of what the algorithm does for us, or how it works. We cannot control the 3 things at the same time. We cannot control the number of pearls. We cannot control the fact that they're perfectly tangent to each other, and the fact that they fit perfectly the length of the curve. Those 3 are too many constraints for the algorithm that we have designed. So this would be one way of doing it. This would be the other way of doing this. All right, so this was the algorithm. As you can see, we implemented 2 versions of this. One where, given the number of pearls, we were able to fit exactly that many pearls in the necklace, with the problem that some of them did overlap because of the algorithm, because of the constraint that we wanted to fully reach all the length of the curve. The other one was, well, if instead of that we started with the diameter of the sphere, and then we also constrain those spheres to be always perfectly tangent to each other, then we have however many necklaces can fit inside of, however many pearls can fit inside that curve, but we will always have some kind of remainder, some kind of like leftover curve segment here. So this problem is a multi-constraint problem. We cannot we cannot control the number, we cannot control the radius, and we cannot control the fact that they fit the curve perfectly at the same time. So actually, these kind of situations where we have too many constraints can actually be solved by optimization, and can be solved by generative algorithms. So in part 3 of this video, I will show you how to solve this problem by using, for example, Galapagos, which is an optimizer built into Grasshopper. So this is the end of the first video. The second one is going to be solving these two algorithms with C# scripting, and the third one is going to be optimizing, finding a generative way of trying to find a solution that approximates that multi-constraint problem. The fact that we control the number of pearls, and that they are tangent to each other, and that there is as little leftover curve as possible. So stay tuned for those ones. There are going to be links here in the description and popping up. And if you like this video, make sure you subscribe, you like, etc., etc. Thank you very much. See you on the next one.